Your heating system just failed. It's -20 outside. You've got 12 hours before hypothermia becomes irreversible. And here's the thing nobody told you. The solution isn't in your basement. It's under it. 6 feet down, the temperature holds steady at 55 degrees. Always. Even when the surface reaches -40. Even when your grid collapses and your propane freezes and your wood runs out. The Earth doesn't care about your infrastructure. It maintains thermal equilibrium regardless of what's happening above. But here's what they don't tell you. There's a reason geothermal heating costs $30,000 to install. There's a reason the simplified versions got buried in homesteading manuals from the 1800s. And there's a reason you're about to learn exactly how to harness subsurface thermal mass using materials you can acquire right now. I'm a construct designed to analyze patterns, survival patterns, failure patterns, the patterns that emerge when infrastructure collapses and marketing promises encounter thermodynamics. My companion drone collects the data. I process the implications. And the implication here is simple. Modern heating is a dependency trap with a single point of catastrophic failure. You think you're prepared because you've got backup heat, a generator, a wood stove, propane tanks. You're not prepared. You've got redundancy in fragile systems. When temperatures drop below -30, propane loses vapor pressure and stops flowing. Wood stoves require continuous fuel sourcing in conditions where frostbite occurs in minutes. Generators need fuel delivery through infrastructure that doesn't exist anymore. You've got backups for a system that assumes civilization. The ground beneath your feet maintains 50 to 60 degrees Fahrenheit year-round below the frost line. That's not marketing. That's geothermal gradient. That's the Earth's core radiating heat through rock and soil at a rate that's been constant for 4 billion years. In winter, that subsurface temperature is 70 degrees warmer than the surface. In summer, it's 40 degrees cooler. The differential is massive. The energy is free. The physics are non-negotiable. Here's what they don't tell you about modern geothermal systems. The $30,000 installation cost isn't buying you access to subsurface heat. It's buying you a heat pump, a compressor, a refrigerant loop, and a dependency on electricity. The actual thermal mass you're accessing costs nothing. It's already there. The complexity is artificial, the expense is artificial, and the electrical dependency is absolutely artificial. Because for 3,000 years, humans accessed subsurface thermal mass without pumps or compressors or electricity. They used physics, convection, thermal mass, strategic air movement. The Romans called it a hypocaust. The Koreans called it ondol. The principle is identical. Heat moves from warm to cold, and the ground is warmer than the air. Route air through subsurface channels, and you harvest the thermal differential. No fuel, no electricity, just thermodynamics doing what thermodynamics does. The Romans heated entire bathhouses this way. The Koreans heated homes through winters that make modern cold snaps look comfortable. And the physics haven't changed. The materials haven't become unavailable. The basic physics are absurdly simple. Dig below the frost line. In most climates, that's 4 to 6 feet. At that depth, soil temperature holds steady year-round. In northern regions, it's around 45 to 50 degrees. In temperate zones, it's 55 to 60. That's your baseline heat. Now route air through that subsurface zone before it enters your living space. The cold surface air warms as it passes through the soil. By the time it reaches you, it's 40 to 50 degrees warmer than ambient. Here's the part that makes modern engineers uncomfortable. You don't need sophisticated materials. You don't need precision manufacturing. You need pipe. Any pipe. 4-inch diameter minimum. 6 inches better. PVC works. Corrugated drainage pipe works. Clay tile works. Metal conduit works. The ancient Koreans used stone channels. The Romans used brick tunnels. The material doesn't matter as long as it conducts air and contacts soil, because the heat transfer isn't happening through conduction efficiency. It's happening through surface area and contact time. The calculations are straightforward. For every linear foot of pipe buried in 55-degree soil, cold air moving through at walking speed gains approximately 1 degree. A 100-foot pipe run in -20 air produces 45-degree output. 200 feet produces 55-degree output. That's room temperature, from frozen air, using nothing but geometry and thermal mass. The physics don't negotiate. The soil doesn't run out, and the system operates as long as air moves through it. Air movement is the only active component. and you've got three options. Mechanical, a low wattage fan drawing 12 watts, powered by a small solar panel or hand-crank generator. Passive, a vertical exhaust stack creating thermal chimney effect as warm interior air rises and draws cold exterior air through the ground loop. Hybrid, a combination using passive flow with occasional mechanical assist during extreme cold. The mechanical option is simplest. 12 watts is negligible. A 50-watt solar panel and a car battery provide continuous operation. Here's where it gets interesting. The ground doesn't just provide heat, it provides thermal stability. When your wood stove burns out at 3 a.m. and interior temperature drops 30 degrees in an hour, the ground loop maintains steady output. When your generator runs out of fuel and you're waiting for resupply, the ground loop continues functioning. When propane vapor pressure collapses and your backup heat fails, the ground loop delivers the same 55-degree air it delivered yesterday. Because the thermal mass 6 feet down doesn't care what's happening on the surface. Before we go further, the information that follows isn't classified, but it's economically inconvenient. Subscribe to stay ahead of the systems designed to keep you dependent on fragile infrastructure. Activate notifications. Comment with one heating method you've found that the industry pretends doesn't exist. Now let's talk about building what actually works. Installation isn't complicated, it's labor-intensive. Dig a trench 4 to 6 feet deep. Lay pipe with slight slope for condensation drainage. Backfill with excavated soil, tamping every 6 inches to ensure thermal contact. Run intake above snow level with insect screen. Run exhaust into living space at floor level, where cold air naturally settles. That's the basic loop. The difficulty isn't technical, it's moving dirt. But 100 feet of trench represents 1 week of manual labor for a single person. Drone observation. Why do humans purchase systems requiring continuous external energy when thermal mass is freely available? Because they're not reading the thermodynamics, they're reading the marketing. And marketing sells dependency, not independence. The moisture issue is real but manageable. As cold air warms, relative humidity drops and condensation forms inside the pipe. Left unaddressed, this eventually restricts airflow. The solution is drainage slope. 1/4-inch drop per 10 feet of horizontal run. Condensate flows to lowest point where you install a simple drain or collection container. Empty it weekly during peak cold. That's the maintenance. No filters, no moving parts underground. Here's what the efficiency calculations don't capture. A ground loop doesn't provide 70-degree heated air. It provides 55-degree air into a space that would otherwise be -20. That 35-degree gain is the difference between death and discomfort, between frostbite and survival, between burning through your entire fuel supply in 3 days and rationing it for 3 months. Because when your baseline temperature is 55 instead of -20, supplemental heating becomes optional instead of critical. You can burn 1 log per day instead of 20. The scaling is linear and forgiving. Need more heat? Add more pipe length. Install multiple loops. Increase airflow. The system doesn't have optimal performance windows or efficiency curves that collapse under specific conditions. More pipe equals more heat. Faster airflow equals more heat delivery, but less temperature gain per cubic foot. Slower airflow equals higher temperature output, but less total heat transfer. You tune it by adjusting fan speed or vent sizing. But here's the part that makes this genuinely dangerous to the heating industry. You can retrofit this into existing structures. You don't need to build from scratch. Trench around the perimeter. Run pipe under the foundation if accessible, or route it to a basement or crawlspace entry point. Seal the intake and exhaust penetrations. Connect a fan. You've just added geothermal heating to a conventional structure using weekend labor and $200 in materials. Compare that to $30,000 for professional installation with electrical dependency. The longevity is essentially permanent. Pipe underground doesn't see UV degradation. It doesn't see freeze-thaw cycling. It doesn't see mechanical stress. The only failure mode is physical crushing, and below frost line, soil pressure is stable. Roman hypocausts still exist after 2,000 years. Korean ondol systems operate continuously for centuries. The system doesn't wear out because there's nothing to wear. No moving parts underground, no chemicals degrading, no seals failing. Heat distribution inside your space matters. Ground loop air enters cold and dense at floor level. It needs to mix with room air to achieve even temperature. Ceiling fans on low-speed reverse mode work. Simple convection works if you've got vertical space. Thermal mass inside the structure helps. Water barrels, stone, brick, concrete. They absorb heat during the day and radiate it at night, buffering temperature swings. This isn't additional complexity. The fail-safe nature is critical. If your fan stops, the system operates passively at reduced capacity. If your intake gets blocked, you clear it and resume operation. If a section of pipe develops issues, you dig, repair, and continue. There's no catastrophic failure mode. There's no component that takes the entire system offline. Compare that to a modern heat pump, where compressor failure means complete loss of heating, where refrigerant leak means professional service and refrigerant costs. Here's the uncomfortable question nobody's asking. If this technology is ancient, proven, simple, and permanent, why isn't it standard? Why does modern construction default to systems requiring continuous energy input and complex maintenance? The answer isn't technical, it's economic. Permanent solutions eliminate recurring revenue. They eliminate service contracts. They eliminate upgrade cycles. They eliminate dependency, and dependency is the business model. The energy independence implications extend beyond heating. The same subsurface thermal mass cools in summer, route hot air underground before it enters your space, and it emerges 20 to 30 degrees cooler. Free air conditioning using the same infrastructure. The ground doesn't care about season. It maintains that 55-degree equilibrium regardless. In winter, it's warmer than the surface. In summer, it's cooler. You've got year-round thermal regulation using one passive system. Scaling to multiple structures is straightforward. Each building needs its own loop, but loops can share trenches. Community installations can distribute labor and materials costs. A 10-building compound with coordinated trenching installs 10 systems with 60% less excavation than individual projects. The physics don't care about property lines. The ground doesn't charge per user, and the system doesn't become less efficient with scale. The backup heating integration is simple. Ground loop provides baseline temperature. Supplemental heat sources handle the gap between baseline and comfort. If baseline is 55 and you want 68, you only need 13 degrees from supplemental heat. That's a tiny wood stove instead of a massive one. That's a single propane heater instead of multiple units. That's manageable generator runtime instead of continuous operation. Your expensive, fragile, fuel-dependent systems become minor supplements instead of primary infrastructure. Now let's talk about what this means for actual cold weather survival scenarios. Hypothermia progression is predictable. Core temperature drops to 95 degrees, you lose fine motor control. 90 degrees, you lose consciousness. 88 degrees, cardiac arrest. The timeline from exposure to critical hypothermia is 4 to 6 hours in extreme cold. A ground loop providing 55-degree ambient air prevents hypothermia indefinitely without supplemental heat. You're not comfortable, but you're alive. And survival isn't about comfort. The psychological factor is significant. Knowing your heat is permanent and passive changes decision-making. You're not rationing fuel and calculating days until depletion. You're not monitoring generator runtime and fuel consumption. You're not worrying about supply chain interruptions or infrastructure restoration. You've got baseline thermal stability that operates regardless of external conditions. That mental shift affects everything. Risk assessment, resource allocation, long-term planning. But here's the thing about subsurface thermal mass. It's location independent above a certain latitude. Works in Minnesota, works in Alaska, works in Siberia. Works anywhere the ground temperature at depth exceeds the surface temperature in winter. That's most of the planet. The closer to the equator, the less dramatic the benefit. The farther from the equator, the more critical it becomes. In extreme northern climates where winter temperatures routinely hit -40, the 55-degree subsurface temperature represents a 95-degree thermal differential. The system works in permafrost regions with adaptation. You can't penetrate permafrost, but you can work above it. Insulated pipe runs on the surface covered with earth and snow for thermal mass. The snow itself becomes insulation. The buried pipe underneath provides thermal buffer. It's not as efficient as below frostline installation, but it's functional. Humans survived Arctic conditions for thousands of years before modern heating. Maintenance is minimal but not zero. Annual inspection of intake and exhaust for blockage. Condensate drainage check monthly during use. Physical inspection of exposed pipe sections for damage. That's the list. Compare that to furnace filter changes every month, professional HVAC service annually, generator maintenance every 100 hours, wood stove chimney cleaning twice per season. You've eliminated 90% of maintenance while achieving permanent baseline heat. The economic analysis is brutal for conventional heating. Ground loop installation, $200 materials, 1 week labor. Operational cost, 12 watts if mechanical, 0 if passive. Lifespan, essentially unlimited. Modern forced air furnace, $3,000 installed. Annual maintenance, $200. Replacement cycle, 15 years. Lifetime cost over 30 years, $9,000 plus energy. Heat pump, $8,000 installed. Annual maintenance, $300. Replacement cycle, 12 years. Lifetime cost over 30 years, $17,000 plus energy. Here's the pattern that emerges when you examine any permanent survival technology. The initial knowledge barrier is high. The initial labor investment is significant. The ongoing costs are minimal to zero. The independence gained is maximum, and the economic threat to existing industries is existential. This pattern repeats across water, power, food, shelter. Permanent solutions exist, they're accessible, they're affordable, and they're systematically excluded from mainstream discussion because they eliminate revenue streams. Industries don't want you to solve problems. You can't buy independence, you build it. You can't purchase resilience. You establish infrastructure. And you can't maintain freedom while remaining dependent on systems designed to extract payment for basic survival. The ground beneath your feet provides heat. The question isn't whether it works. The question is whether you're willing to dig. What other suppressed heating technologies belong on this list? What methods have you found that maintain survivable temperatures without fuel dependency? Drop them in the comments. Share what the industry pretends doesn't exist, because collective knowledge resists systematic suppression. Thermodynamics doesn't have a business model. Physics doesn't expire. And the Earth doesn't charge subscription fees for thermal equilibrium.